All right, welcome to Secondary Math 2, classifying numbers in the number system. So in our last unit, we talked about classifying polynomials, but right now we're going to be talking about classifying numbers. So we're going to first start with the real number system, okay? Eventually we will talk about imaginary numbers, okay? But we'll start with just the real numbers. So the most specific set, so these are all types of numbers, and I'll list some examples and we'll go over those. But we'll start with the natural numbers. So natural numbers are the counting numbers. So if you started to count, you would start 1, 2, 3, 4, and so forth. These are the counting numbers. All right. Some examples of how you may see a natural number could be something like 5. Okay. You could also have these are examples. We could have some other examples, could be something like 4 halves. So if you simplify, you end up getting 2. Right. So sometimes you may see it as a fraction, but if you simplify it, we'll see what it really is. Okay, I guess that's what I'm trying to say. All right, another example could be like the square root of 4. Any perfect square root of 16 would be 4. Square root of 81 would be 9. So if you simplify that, that would give us 2. So one of the things I would suggest is when you get something in there, asking what is the most specific set, or what set does it belong to? Plug it in your calculator and see what it looks like. Okay. Okay, I think that's pretty good. Next we have the whole numbers. So whole numbers are the same as natural numbers, except they have a whole. And that whole is a 0. So we have 1, 2, 3, 4, ... Okay? So all of... okay, so I guess I should say natural numbers, all natural numbers are also whole numbers, okay? And you can totally see that because this is 1, 2, 3, 4, 5, and we have 1, 2, 3, 4, 5, ... Okay? So the natural number is part of a whole number, and a whole number is part of an integer, okay? They kind of build upon each other. So another example of a whole number would be something like a fraction, 0 over 2 or something like that. If you plug that in your calculator, you'd still get 0. All right? And then you would also have all other whole numbers, also other examples could be the natural numbers. Okay? Because all whole numbers are not, all natural numbers are whole numbers. Okay, next we have integers. Integers are all the whole numbers except also their negatives. So, for example, ... -3, -2, -1, 0, 1, 2, 3, ... for infinity, okay? Both sides. So as long as they're whole numbers that are either positive or negative, that's what an integer is, okay? So basically we have the same examples that are below us, except they can also be negative. Okay? Next we have rational numbers. Rational numbers are any numbers that can be written as a fraction. For example, 1/2 is equal to 0.5. So 1/2 would be a fraction, but a decimal can also be written as a fraction. So if I gave you, is 0.5 a rational number? Well, you could say yes, because it can be written as a fraction, 1/2. All right. Another example could be something like 1 over 11, which is a fraction. But maybe the problem doesn't give you the 1 over 11. Maybe they give you something like 0.090909, and with a bar on top, which tells you it keeps going forever. All right? So with decimals, decimals are always rational if the decimals end or they have a pattern that goes forever, okay? So decimals that end or have a pattern. Okay, so that's what rationals are. Okay, over here we have irrational numbers. Irrationals are decimals that go forever. Decimals that go forever and have no pattern. Okay, so for example, some most common irrational numbers would be something like pi. Okay, pi, I just want to write those down so we can look at those. So if we put pi into our calculator and push enter, it would tell us that would be 3.14159 2654 ... Okay, your calculator won't go forever. Okay, it will round probably to that. I don't know if it rounded up or rounded down to 4, but it has no pattern. Another example would be a square root that is not a perfect square. For example, square root of 2, square root of 3, square root of 10. Okay, one way to check would be to plug it in your calculator. All right, and it would give you a decimal, 1.41421356 ... Okay, again, it goes forever and has no pattern. All right. Okay, so let's look at some examples. Okay, it says name the set or sets. Okay, so if it has more than one set, then we should list all of those that each number belongs to. Circle the most specific set. So again, like I suggested, if you have a number, you should maybe plug it into your calculator and see what you'd get. So here you'd get 9. So we'd go through the list. Okay, the most specific, the broadest set would be the real number system. So we'd start with the largest. So we'd say real. Next we have rational. Okay, is 9 rational? For sure it is. You could write it as a fraction. You could divide anything by 1 and not change anything. So that can be written as a fraction. All right, next we have integers. Okay, is it a whole number that, does it not have a decimal? It doesn't have a decimal, so then it's going to be an integer. Okay, it's a whole number that could be positive or negative. We know that it's a whole number because it's positive and it's doesn't have a decimal. And then we have natural numbers. Okay, and since it's not 0, we know that it's natural, so we would circle natural. All right, some of you may not want to write those letters every time on your homework, so I'll give you, show you how you can abbreviate, okay? Real, the abbreviation for real is this R. It's like a script R. Okay, even if you just wrote an R, that would be fine. Okay, to identify rational, well, since we already have an R, we use Q. Right? Q has something to do with the German language. It has the word quotient, which is another word for a fraction. Okay, integers, also because of the Germans, we use a Z. Whole numbers, we use a W. And natural numbers, okay, we use an N. So the only ones that are kind of different is the rational and the integers. Integers. I don't know. Okay, so if you wanted to, you could rather than writing down everything down, you could just write down R, Q, or Z. Sometimes I forget to. Okay, W, and then natural, okay, and then you would circle that. Okay, and it doesn't have to be a column, it can be a row, either way, okay? So let's just go over. I would pause if you can and try and do the rest of these and then see how you did, okay? So here we can simplify that. That would just be 0. So again, we'd write down real, integer, or rational, sorry, rational, integer, and whole. And whole would be our most specific set because natural is not, 0 is not a natural number. Okay? Again, here you could plug that in your calculator. Whenever you have roots, I would just put it in your calculator. So the square root of 279 divided by 3. And with my calculator, sometimes you need to switch it from, so you can get a decimal, but anyways. That ends up giving us 9.643650761, ... Okay? So we would definitely say that it is real. It's still real. Everything we've been talking about so far is real. And then we would have irrational, which here we will call it, if you want to abbreviate, then maybe do, see, we're going to be doing imaginary. So, well, let me check really quick, if you don't mind. I'm just going to see if there is an abbreviation for irrational. Let's see. It says here, I don't know if this is true, but it says the set of irrational numbers is expressed as the set of all real numbers minus, so R minus. But I don't know, I would maybe just do something like IR for irrational, okay? And then we'd circle that. That's interesting, okay? So it's like anyways. Okay, next, plug that in your calculator. I think you end up getting 15. So here you would go and do real, rational, integer, whole, and natural, and circle natural. Okay. This one, you'd maybe plug that in your calculator, see if it can be simplified to integer or a natural number. Okay. I mean, the way it looks, it's a fraction, and we know that it's rational because it's written as a fraction. But we'll divide that by 64, and we end up getting 2.75. So it has a decimal that ends, which means it is, we have it real, and then we have rational. Let's circle that. Next one would also get a decimal. We'll just skip that one. G here, we would end up getting -7. So we'd know that it's real. We know that it is rational. We could divide that by 1 to make it be rational. And we know that it's an integer, because it is a whole number that is negative. It's not whole because it's not positive, so and we'd be done. So next we have pi plus 3. Well, pi plus 3, if you plug that in your calculator, it'd be 6.1415 ... with no pattern. So we'd say real and then irrational. Okay. All right, so let's go over some of these example 2. Determine if each statement is always, sometimes, or never true. Okay, so pause and see if you can answer these before I go over them. If a number is rational, so an example of a rational would be something like 1/2. Okay, or it could also be something like 2. Okay, that could be rational as well. Okay, if a number is rational, it can be irrational too. Okay, so that's kind of like saying Can it have a decimal that has a pattern and not have a pattern at the same time? So here that would say never. Okay. Integer, so an integer is something like -1 or 2, that would be an example of an integer. Is an integer a whole number? Okay, well, for this example, 2 is a whole number, but -1 is not a whole number. So you would say sometimes. Okay, so when we do sometimes, let's just say some examples of true and false. So we already kind of did that. True would be something like 1, 2, 3, or any of those numbers. Or I guess you could have 0, 2. And anything that you couldn't do would be something like -1, -2, -3. Okay, and those would make it be false. Okay, a natural number, so like a natural number would be something like 1 or 2, okay, is a real number. All right, well, what we've been talking about, everything we've been talking about is real, so here we'd say true. And then the last one, a whole number could be 0, 1, 2, 3. Now, if you have to do these kind of problems, maybe give some examples. I think that's a really good idea on the test. So a whole number is a natural number. Okay, well, a natural number is 1, 2, 3. So here we'd say sometimes. It would be true, or I guess the only time it would be false would when it was 0. Okay, true would be anything else. 1, 2, 3. That could be a whole number. Okay. All right. Next page. Just some more examples. Pause again and see if you can write these down. Here they only want the most specific set. Okay. So the first one, -5/6. Okay. It can't be simplified, so we can't have an integer. It's going to be a decimal. If we did -5/6, that would give us, as a decimal, would be -0.8333 forever. Okay, and since it has a pattern, then yes, we could also, if we just looked at this without having the fraction, we could say yes, that is also irrational. Okay, so it's written as a fraction, or it can be written as a decimal that has a pattern. Okay, next, this, since the decimal ends, that we know it's rational as well. Okay, and you can write any decimal, even if it goes forever, which is kind of cool. You can write any decimal that has a pattern or ends. It can be written as a fraction, which is really cool. Like for example, 35.99. Okay, if you divide that by 1, and if we move the decimal over twice, and then we move the decimal over twice again, and that would give us 3,599 over 100. That would give us the exact same answer as 35.99. Okay, anyways, interesting, perhaps, I don't know. Again, we have a fraction, can't be simplified, so it's going to be rational. Square root of 16 is 4, so we would say natural. 12 over 3 is also 4, so again, natural. Square root of 10, if you plug that in your calculator, you'd find that you would get a decimal. Let me see what that decimal is. Oops. Sorry, 1 sec. There we go. So that would give us something like 3.16227766 ... So this would be irrational. Okay, that's pretty close to pi, 3.14. Okay. All right, next, no pattern, irrational, and pattern, so rational. Okay. Okay, next, this is more like mark all sets. So -1, it's real, yes, it's rational, and it is an integer. Okay, it's not whole because it's not negative, or I mean it is negative. Okay, 5 is a whole number, and it's also a natural number because it's not 0. Okay, 1.5 is a decimal, so, and it can't be simplified to make like a whole number or an integer. 6 to the 0, remember anything to the 0 is 1, so that brings us all the way to natural. Okay, had a lot of students say that 6 to the 0 is 0. Pi, we already talked about pi. It is real, but it is irrational. Same as the square root of 17. 0 is a whole number. -8 is an integer. Square root of 81 is 9. This is 9, so it would be natural. 2.7 is rational, and 1 divided by 7 is also rational. Okay, had some students, which is good to look at. If you do 1 divided by 7 and have it as a decimal, you end up getting 0.142857, and then it starts again. Okay, so on my calculator, it actually stops here and puts a bar on top of it, telling it that it is repeating. But so you notice that, I mean, this is what, six numbers. Okay, sometimes the pattern gets kind of big, so make sure you check it. Don't look at the first 4 or 5 and say, oh, there's no pattern, it must be irrational, because we know that 1/7 is a fraction, or is rational. Next we have circle true or false. So all integers are rational numbers. Okay, so integers are like -1 or 2. Okay, all integers are rational numbers. So I would say true, because we could divide that by 1, and that would be rational. It would be a fraction. Okay, next we have all negative numbers. So negative numbers are like -1, -2, etc. Are integers. Okay, well, okay, maybe I should have given another example. Okay, another negative number could be -0.5. Okay, and -0.5 would not be an integer. Okay, and since we're talking about all, we'd need to say false. Okay, because some negative numbers are integers, but some of them are not. Okay, next, 3.87655 is a rational number. Okay, some people may look at that and say, well, it has no pattern. Okay, but you also notice that it doesn't have a ... at the end. So that means that it ends. So it's a decimal that ends, so therefore it is a rational number. It can be written as a fraction. Square root of 7 is a real number, true. Everything we've talked about so far is real. It's also irrational, so don't get real and irrational mixed up, or real and rational. All fractions are integers. So a fraction could be an integer, but a fraction could also not be an integer. Not integer. Okay, integers can't have decimals, can't be. Okay, so here would say false, because all of them are not. Some of them are, but some aren't. Okay. All right. Next, we're going to talk about the complex number system. So I'm going to try and speed this up a little bit so it doesn't go forever. Okay, so let's do some examples. 5 squared, 25. 2 squared is 4. -2 squared is 4. -100 is 100, or 110. Sorry, a -10 squared is 100. Okay, so it looks like no matter what you do when you square, it's always going to be positive. Okay, and we kind of talked about that before. So if you did, anyways, I'll just keep going. So when squaring a number, it almost seems like it's always positive. Positive. Okay. It seems like we can't multiply a number by itself and get a negative number, but imagine there could be such a number. Call it imaginary. That could do it. So basically, mathematicians were trying to solve some problems, and they weren't able because of the negative in the root. And so they decided to come up with an alternative number system, and that's called the complex number system. And that allows us to take care of negatives inside of a root. So, and that is called the imaginary number. Okay, so the imaginary numbers were once thought to be impossible, and because of that they were called imaginary. But some people researched, and they discovered that they were actually very useful and important. And so it is now part of mathematics, but the name imaginary stuck. So that's why we use the word imaginary. I mean, it's not really imaginary, it's just a different number systems, okay? So a complex number is a number with a real part and an imaginary part. Okay, so for an example, 1 minus 2i. So in that example, the real part would be 1, and the imaginary part would be negative 2. And I is equal to the square root of a negative 1. Okay, so here's some more examples. Complex numbers, 3 plus 2i. It has its real part is 3, and the imaginary part is 2. 5 is a complex number. It has a real part and an imaginary part that is 0, so we don't show it. I mean, it's just like if you have x plus 0, you would simplify it, and all you would write would be x. Same thing for this situation. It's complex, but it only has a non-zero imaginary part. Okay? So, what we can get from this is that let's write that down, every number is complex. Okay? So looking back to here, when we listed these things, we really should be writing a C for complex very first. Complex. Okay, I didn't spell that well, but anyways, you know what I'm saying. So on your homework or quizzes, you would want to write complex first, complex then real, or you could go complex imaginary. And if it is a number that is both, like this, then you could just say it is just complex. Okay? I mean, it does have a real part and an imaginary part, but so we'll have problems on the quizzes and perhaps on the test where we'll need to identify the real and imaginary parts of a complex number. So again, this would be the real part, this would be the imaginary. Okay? Again, real, imaginary. You always have the sign too, so make sure you have that. This would be the real, and this would be the imaginary. Okay? And then we just have a couple things left. Okay, imaginary numbers. So I want to switch this next year, but anyways. Okay, I. So I, we already it's on that paper before. I is equal to a negative 1. So like I said before, we wouldn't be able to take the square root of a negative 1, but since we're using the complex number system, we can use I as the square root of -1. All right, and we'll be using this I squared in the future, but you can kind of think about that. How could we calculate I squared? Okay, so if we square root both sides, the square and the square root cancel, and we'd end up getting -1. Okay, I'm just gonna. Okay, anyways, but we'll just be using this right now for your homework. So use I equals the square root of -1 to simplify each radical expression. Okay, so let me kind of explain this. And this is the best way that I can explain it, okay? Would you believe that we could write this as -1 times 25 inside of here? So basically we're kind of like unsimplifying it, okay? And under multiplication, and only under multiplication and division, can we separate these? So we could do -1 times the square root of 25, okay? So we'd still here we'd get the same solution, okay? But we know what the square root of -1 is, that's I, and we know what the square root of 25 is, which is 5. Okay, convention, we should write the I after the coefficient, and that would give us our answer, 5I. So from going on, I wouldn't require you to do this part, but you could just say, well, square root of 81 is 9, and we have a negative inside, so we're going to have an I. Okay? Again, this would be 11I. So you could just plug in, if you didn't know what the square root of 121, then just plug it in, just without the negative. And that will give you the 11. And then our negative, square root of a negative, gives us an I. So here we've got 4I, 10I, and I think it's 13I. Okay? So that shouldn't be too bad. So here's just a go over of everything we've done. The complex number system has all of this in there, okay? I mean, either you'll go from complex to real, and then real to rational or irrational, and then you'll follow down until you can't get any further. Or you may go to complex and imaginary, if it's purely imaginary, okay? Or if you have something that is real and imaginary, then you could just stop at complex, okay? All right, well, hopefully that helped. Let me know if you have any questions.